Hello, dear companion of this journey. Where are you right now? Perhaps in your room, with the soft light of evening filtering through the curtains. Or maybe in a comfortable armchair, with the world outside following its quiet rhythm. What time is it where you are? And how do you feel in this moment? Relaxed? Curious? Ready to embark on an adventure that's happening right under your nose but is completely invisible to your eyes? I have a story to tell. A narrative that unfolds in every atom of your body, in every strand of hair, in every drop of blood that circulates through your veins. It's a dance. An invisible dance, silent, yet so fundamental that without it you simply wouldn't exist. It's the dance of electrons. Have you ever stopped to think that everything you touch, everything you see, everything you feel is actually the result of a microscopic choreography? That the chair you're sitting in, the air you breathe, the screen where you might be reading these words, all of this is sustained by billions and billions of tiny invisible dancers spinning and leaping in a performance that never stops? Close your eyes for a moment. Feel the weight of your body, the texture of the surface where you're resting. Now imagine that I could shrink you down to the size of an electron. Suddenly, you would find yourself in a completely different universe, where the laws of physics we know behave mysteriously, where particles can be in two places at once, where reality itself seems to dance between the possible and the impossible. This microscopic world isn't just a technical detail of science. It's the foundation of everything. It's the secret behind the color of the sky, the hardness of diamond, the conductivity of copper, the life that pulses in every cell of your body. It's the reason you can feel, think, dream, and exist. What if I told you that this dance began billions of years ago in the hearts of stars, and that it will continue long after you and I have departed? That it is, at the same time, the oldest and most modern of arts? That it's governed by laws so elegant they make mathematicians weep with beauty, and so mysterious they still leave physicists perplexed? Let's embark on this journey together. Let's dive into the invisible world where electrons dance their eternal choreography, where the infinitely small builds the infinitely large, where uncertainty is the only certainty, and where beauty hides in the fundamental rhythms of existence. Just over a century ago, humanity didn't even know these dancers existed. Imagine that, for thousands of years, philosophers, alchemists, and thinkers speculated about the ultimate nature of matter, but never imagined that all reality depended on an invisible dance. It was in 1897 that Joseph John Thomson, an English physicist with an imposing mustache and curious eyes, discovered the first dancer. He was working with glass tubes filled with rarefied gases, passing electric currents through them. What he saw were mysterious rays, beams of something that curved when exposed to magnetic fields, something smaller than any atom ever imagined. Thomson called these particles corpuscles, but the world knew them as electrons. Have you ever wondered where this word comes from? Electron in Greek means amber, that golden resin that ancient Greeks rubbed on animal skins and which attracted small objects. They didn't know it, but they were already witnessing the dance of electrons. Centuries before discovering that the dancers existed, but Thomson's discovery was just the first step. Soon other scientists began to realize that this dance was far more complex than they had imagined. In 1909, Ernest Rutherford, a New Zealander with a powerful voice and magnetic personality, conducted an experiment that would forever change our understanding of the world. Rutherford bombarded a thin sheet of gold with alpha particles, small atomic projectiles. He expected these particles to pass through the sheet like bullets through a cloud, but some ricocheted back as if they had hit something solid and dense. That's when he realized the atom wasn't a homogeneous mass, but rather an almost empty space with a tiny, dense nucleus at the center. And where were the electrons in this new vision? Dancing around the nucleus like planets around the sun. Or at least that's what Rutherford imagined. He couldn't know that he was only scratching the surface of a much deeper mystery. Can you imagine the sensation of these pioneers? They were literally discovering a new dimension of reality. It was as if, after thousands of years of observing shadows on a cave wall, someone suddenly turned on a flashlight and revealed that the shadows were just reflections of a three-dimensional dance happening behind them. But the true revolution was yet to come. Because electrons, as we would soon discover, don't follow the rules we know. They dance to music that our intuition cannot hear, in rhythms that challenge our understanding of time and space. Around 1920, physicists began to realize that something was fundamentally wrong with the image of electrons orbiting the nucleus like planets. If that were true, electrons should constantly be losing energy, spiraling toward the nucleus until every atom collapsed in a fraction of a second. But this clearly wasn't happening. You're here, I'm here, the universe continues to exist. It was then that a new understanding began to emerge, so strange and beautiful that it still challenges our imagination today. Electrons don't orbit, they dance. And this dance follows completely different rules from those we know in the visible world. Max Planck, a German physicist of serious appearance but revolutionary mind, was the first to realize that energy doesn't flow continuously, like water from a faucet, but in small packets, like drops. He called these packets quanta, and thus quantum mechanics was born, the science that governs the dance of electrons. Niels Bohr, a Dane with a gentle smile and deep thought, was the first to apply these ideas to atoms. He proposed that electrons can only occupy certain shells or energy levels, like steps on an invisible ladder. They can jump from one step to another, but can never stop between steps. Have you ever thought about this? Imagine that you could only be on the first floor of a building, or the second or the third, but could never stop in the middle of the staircase. This is how the dance of electrons works. They jump instantaneously from one level to another. Without passing through the intermediate space, it's as if they teleported. But the strangeness was just beginning. Werner Heisenberg, a brilliant young German, discovered something even more disturbing. You can never know, at the same time, where an electron is and where it's going. The more precisely you try to measure its position, the less you can know about its speed, and vice versa. This isn't a limitation of our technology. It's a fundamental property of reality. Electrons don't have a defined position until you observe them. They exist in a kind of ghostly state, a cloud of possibilities that only becomes real when you decide to look. Erwin Schrödinger, an Austrian physicist with a love for philosophy, developed an equation that describes this probabilistic dance. His equation doesn't tell us where the electron is, but where it probably is. It's as if each electron were a musical note resonating at multiple frequencies simultaneously, creating chords of possibility. What if the universe were different? What if electrons followed the rules of our everyday world? There would be no chemistry, no life, no colors, no you. Quantum uncertainty isn't a flaw in nature. It's its most essential characteristic. Now that we know the basic rules of the dance, let's observe the dancers more closely. Electrons don't orbit the nucleus like planets. Instead, they inhabit what physicists call orbitals, regions of space where they're most likely to be found. Imagine a cloud of perfume spreading through the air. You can smell it more strongly near the source, but you can't say exactly where each perfume molecule is. That's what orbitals are like, clouds of probability where electrons dance. But these clouds have fascinating shapes. The simplest orbital, called S, is a perfect sphere centered on the nucleus. It's as if the electron danced in an invisible bubble, sometimes closer to the center, sometimes farther away, but always maintaining its spherical shape. The p orbitals are even more interesting. They're shaped like dumbbells, with two lobes separated by a node where the electron can never be. It's as if the dancer had two favorite dance halls, separated by an invisible wall that it never crosses. Have you ever wondered why atoms have the properties they have? Why carbon can form 4 bonds? Why oxygen needs 2 electrons to feel complete? The answer lies in the geometry of this dance. Orbitals organize themselves in space in specific ways, creating a 3-dimensional architecture that determines how atoms interact. The d orbitals are even more complex, with shapes that resemble 4-leaf clovers or donuts. And the f orbitals? They're so complicated that chemists need computers to visualize them. They're like abstract sculptures made of pure probability. But here's what's truly magical. These shapes aren't arbitrary. They emerge naturally from the laws of quantum mechanics, like harmonies that arise from a symphony. Each orbital is a solution to Schrödinger's equation, a note in the cosmic score that governs the dance of electrons. And within each orbital, electrons do something even stranger. They spin not in the sense we know, but in a quantum property called spin. It's as if each electron were a tiny top, but a top that can only spin in two directions, up or down. And here's the crucial detail. Two electrons can only share the same orbital if they spin in opposite directions. Wolfgang Pauli, an Austrian physicist famous for his fierce criticism and relentless precision, discovered this rule. Pauli's exclusion principle says that there cannot be two identical electrons in the same place. It's like a cosmic etiquette rule. Dancers can share the same space but can never make exactly the same movements. This simple rule has enormous consequences. It's responsible for the structure of the periodic table, the stability of matter, the very possibility of chemistry. Without it, all electrons would crowd into the lowest orbital, and the universe would be a very different and much simpler place. Now, let's broaden our view and observe how these individual dances combine to create the architecture of atoms. Each element in the periodic table is like a different orchestra, with its electrons playing specific instruments in unique arrangements. Hydrogen, the simplest of all elements, has only one electron dancing alone around a single proton. It's like a solitary dancer in an empty ballroom, free to express all the elegance of quantum mechanics without distractions. Helium adds a second electron, but still keeps things simple. The two electrons share the same spherical orbital, but with opposite spins like two ice skaters spinning in opposite directions. Helium is stable, satisfied, almost zen in its completeness. But when we get to lithium, the dance becomes complicated. The third electron cannot join the other two in the first orbital. Pauli's principle doesn't allow it. It must find a new space, a new energy level. It's as if the first table at the restaurant were full, forcing the third guest to sit farther away. As you add more electrons, the dance becomes increasingly complex. Carbon, with its 6 electrons, has 2 in the first level and 4 in the second. But these 4 outer electrons don't behave as you might expect. They hybridize, mixing different types of orbitals to create new dance patterns. Have you ever wondered why diamond is so hard? The answer lies in the dance of carbon's electrons. They organize themselves in a perfect three-dimensional structure, where each carbon atom is bonded to 4 others in a tetrahedral pattern. It's as if the electrons were circus artists, creating a human pyramid of impressive stability. Silicon does something similar, but its electrons dance at higher energy levels, creating weaker bonds. That's why silicon is fundamental to electronics. Its electrons are more easily persuaded to move, creating the currents that power our computers. And iron? Iron has a completely different dance. Its outermost electrons inhabit the complex d orbitals, creating magnetic properties that allow it to be attracted to magnets. It's as if some electrons were classical ballet dancers, while others preferred flamenco. Transition metals, like iron, copper, and gold, all have electrons in partially filled d orbitals. This gives them unique properties: electrical conductivity, malleability, the ability to form colored compounds. It's as if each metal were a different musical instrument, producing unique sounds when electrons are stimulated. But perhaps most fascinating is how this atomic architecture repeats in patterns. Dmitry Mendeleev, a Russian chemist with an imposing beard and prophetic vision, noticed that the properties of elements repeated at regular intervals. He organized the elements in a table that revealed this periodicity long before anyone understood why it existed. Today we know that the periodic table is like a map of the electron dance. Each row represents a new energy level being filled. Each column groups elements with similar arrangements of outer electrons. It's a visual symphony of quantum mechanics, a poem written in the language of chemistry. Now let's explore how this invisible dance creates something even more extraordinary: life. You're breathing right now, and each breath is possible thanks to the dance of electrons. The oxygen entering your lungs, the carbon dioxide you exhale, the hemoglobin that transports gases through your blood, all of this is choreographed by electrons. Oxygen is an element voracious for electrons. Its atoms have 6 electrons in the outer shell, but want 8. It's as if they were dancers anxious to complete their performance, always looking for partners to form perfect pairs. When you breathe, oxygen's electrons dance with carbon's electrons in glucose, releasing energy that keeps every cell in your body functioning. This is cellular respiration, an elaborate dance where electrons pass from molecule to molecule, descending an energy staircase like water falling down a waterfall. At each step, a little energy is captured and stored in the form of ATP, the energy currency of life. And proteins? Proteins are like great theaters where thousands of electrons dance in complex choreographies. Each amino acid is like an individual dancer, but when they join in long chains, they create performances of impressive sophistication. Hemoglobin, for example, has an iron atom at its center, surrounded by a structure called the heme group. Iron's electrons dance in a very specific way, creating a perfect place for oxygen to bind. It's like a cosmic ballroom dance, where iron invites oxygen to waltz through your circulatory system. But perhaps the most impressive example is photosynthesis. In the green leaves around you, an extraordinary dance happens every second. Electrons in chlorophyll absorb energy from sunlight and are excited to higher energy levels. It's as if they were dancers receiving an extra boost of energy, allowing them to jump higher and move faster. These energized electrons then pass through a series of molecules in a transport chain, like dancers passing a torch in an Olympic ceremony. With each pass, a little energy is captured and used to build glucose molecules from carbon dioxide and water. Have you ever stopped to think that the food you eat is literally solar energy captured by electrons? Every sugar molecule, every grain of starch, every drop of vegetable oil, all of this is the result of electrons' dance transforming light into matter. And DNA? DNA is like a musical score written in the language of electrons. The nitrogenous bases, adenine, thymine, guanine, cytosine, recognize and bind to each other through interactions between their electrons. It's as if each base were an instrument that can only play in harmony with its specific partner. When DNA replicates, electrons dance to separate the two strands, exposing the bases so new complementary ones can bind. It's a choreography so precise that errors occur less than once in every billion steps. Imagine a ballet where a billion movements happen almost always perfectly. And enzymes? Enzymes are like molecular choreographers, guiding the dance of electrons to accelerate chemical reactions. They create environments where electrons can move more easily, reducing the energy needed for reactions to occur. Even your thoughts depend on the dance of electrons. The nerve impulses traveling through your brain are waves of electrons moving through specialized channels in cell membranes. Every thought you have, every memory you form, every emotion you feel, all of this is orchestrated by electrons dancing in specific patterns. The electricity that lights your home, that powers your devices, that makes our modern civilization possible. All of this is simply electrons dancing on a grand scale. But before we explore technology, let's understand how this dance organizes itself in different materials. In metals, electrons are like dancers in a giant ballroom. They don't belong to any specific atom but form what physicists call a sea of electrons. Imagine a crowd of people at a party, moving freely between different groups, never staying in the same place for long. That's how electrons behave in copper, aluminum, gold. When you apply a potential difference, a voltage, it's like slightly tilting the ballroom. Electrons begin to move preferentially in one direction, creating an electric current. It's a directed dance, organized, but still fundamentally based on the random movement of individual dancers. In insulators like glass or rubber, electrons are firmly attached to their atoms like dancers chained to their chairs. No matter how much you try to persuade them to move, they resist, maintaining their positions. That's why you can hold a copper wire by its plastic sheath without getting shocked. The electrons in the plastic simply refuse to dance. But semiconductors? Semiconductors are where the dance of electrons becomes truly sophisticated. In pure silicon, electrons are trapped in covalent bonds like couples dancing a very formal waltz. But when you add impurities, phosphorus or boron atoms, the dance changes completely. Phosphorus has an extra electron that has no partner to dance with. This lone electron is relatively free to move, creating what we call an untype, negative, semiconductor. Boron, on the other hand, has one less electron, creating a hole in the dance structure. This hole can be filled by a neighboring electron, which in turn creates a new hole, and so on. It's as if there were an empty chair and a row of dancers, and this chair apparently moved as people reorganized. When you join N-type and P-type silicon, something magical happens. The extra electrons from the N side want to dance with the holes on the P side, creating a region where electrons move in only one direction. You've just created a diode, a device that allows current to flow in only one direction, and the transistor? The transistor is like a gate controlled by electrons. You can open or close this gate by applying a small voltage, thus controlling a much larger current. It's as if you were a conductor capable of controlling an entire orchestra with small gestures of your baton. This is the basis of all modern electronics. Your computer, your smartphone, your television, all are composed of billions of tiny electronic gates, opening and closing millions of times per second, processing information in the form of electrons dancing or not dancing. And light? Light is created when electrons jump from higher to lower energy levels, releasing the extra energy as photons. It's as if they were dancers jumping from a higher stage to a lower one, and in the process creating flashes of light. In LEDs, electrons are forced to jump across a pion junction, and each jump produces a photon. The color of the light depends on the amount of energy released, which in turn depends on the materials used. It's a choreographed dance to produce specific colors: red, green, blue, white. Have you ever wondered why different materials produce different colors when heated? It's because electrons in each material have their own unique energy levels, like musical instruments with their own characteristic notes. Sodium produces yellow light, copper green light, lithium red light. Each is a unique signature of the electron dance. Now, let's dive into the most mysterious aspects of the electron dance. The quantum phenomena that challenge our intuition and show us that reality is much stranger than it appears. Have you heard of the famous double-slit experiment? It's one of the most important experiments in physics, and it reveals something deeply disturbing about the nature of electrons. Imagine you have a wall with two parallel slits, and you shoot electrons toward this wall. On the other side, you place a detector to see where the electrons arrive. If electrons were just particles, like tiny balls, you would expect to see two groups of impacts, each corresponding to one of the slits. But that's not what happens. Instead, you see an interference pattern, alternating bands of many and few electrons, like waves created by two stones thrown into a lake. This means that each electron somehow passes through both slits at the same time, interfering with itself. It's as if a dancer could be in two places at once, creating an impossible choreography. But here's the strangest part. If you place a detector in front of one of the slits to see which path the electron actually takes, the interference pattern disappears. The simple act of observing fundamentally changes the electron's behavior. It's as if the dancers were shy and changed their performance when they realized they were being watched. This isn't a poetic metaphor, it's literally what happens. Observation changes reality. Electrons don't have a defined trajectory until you observe them. They exist in a superposition of all possible paths, dancing in multiple realities simultaneously. Einstein hated this idea. He said that God does not play dice with the universe, but quantum mechanics suggests that maybe God plays very sophisticated dice. Randomness isn't just a consequence of our ignorance. It's a fundamental property of reality. And there are more mysteries. Electrons can become entangled with each other, creating connections that persist regardless of distance. If you have two entangled electrons and measure the spin of one, you instantly know the spin of the other, even if it's on the other side of the universe. Einstein called this spooky action at a distance, but experiments have confirmed that entanglement is real. It's as if they were twin dancers who, no matter how far apart, always move in perfect synchronization. Have you ever thought about this? That perhaps the separation we perceive between things is just an illusion created by our macroscopic perspective? That, at the fundamental level, everything might be entangled in a unique cosmic dance? And there's Heisenberg's uncertainty principle, which tells us we can never simultaneously know an electron's position and velocity with perfect precision. It's not a technological limitation, it's a fundamental property of nature. It's as if electrons were dancers who refuse to follow a completely predictable choreography. This has profound implications. It means the future isn't completely determined by the past. There's always an element of uncertainty, a margin for the new and unexpected. The very creativity of the universe might be rooted in quantum uncertainty and quantum tunneling. Electrons can pass through barriers that classically should be insurmountable. It's as if they were dancers capable of walking through walls, appearing on the other side without classical explanation. This phenomenon is essential for many modern technologies, including computer chips and lasers. Perhaps most disturbing is that the very notion of an individual particle may be an illusion. In quantum field theory, electrons are seen as excitations in a field that permeates all space. It's as if the entire universe were an ocean and electrons were waves in that ocean. You can't really separate a wave from the ocean. It is the ocean manifesting locally. This suggests that perhaps there are no fundamental things, only patterns of activity in universal fields. You, I, the stars, the planets, we're all complex patterns of excitation in this fundamental cosmic dance. Look around you. See the colors that paint the world, the blue of the sky, the green of leaves, the red of a rose, the gold of the sun. Every color you see is a note in the visual symphony created by the dance of electrons. But have you ever wondered where these colors come from? Why is the sky blue and not green? Why are leaves green and not blue? The answer lies in the dance of electrons interacting with light. When a photon of light encounters an electron, one of three things can happen. The electron can absorb the photon and jump to a higher energy level, it can reflect the photon, or it can let it pass through. It's like a dancer choosing whether to accept or decline an invitation to dance. The blue of the sky is perhaps the most poetic example of the dance of colors. Air molecules are very small compared to the wavelength of light, but they interact more strongly with blue light than with red. It's as if they were small dancers who prefer fast-tempo music. Blue light is scattered in all directions, painting the sky this majestic color. At sunset, when light has to travel through more atmosphere to reach you, almost all the blue has already been scattered, leaving only reds and oranges. It's as if the orchestra of atmospheric electrons had played all the high notes during the day, leaving only the low notes for the evening symphony. And plants? Plants are masters in the art of selecting colors. Chlorophyll absorbs mainly red and blue light, but reflects green. It's a brilliant evolutionary choice. Green is right in the middle of the visible spectrum, where the sun emits the most energy. Plants basically say no, thank you to green, using it as a visual indicator of their health, while capturing the energies they really need. But here's something fascinating. Plants could have evolved to be black, absorbing all visible light. It would be more energy efficient. So why didn't they? One theory is that it would be dangerous. Absorbing all solar energy could overheat the leaves. Another is that reflecting green helps regulate temperature and prevents damage to the delicate mechanisms of photosynthesis. Have you ever wondered why different materials have different colors? It's because electrons in each material have their own dance preferences. In copper, electrons love to absorb blue and green light, reflecting mainly the red-orange we see. In gold, the electronic configuration is slightly different, absorbing blue but reflecting yellow. And pigments? Pigments are like specialized choreographers, organizing electrons in ways that create specific colors. The red of blood comes from iron in hemoglobin, whose electrons dance in a way that absorbs green and blue. The blue of the sea on clear days is both light scattering and selective absorption of longer wavelengths by water. Colors can also change when electrons change their dance. The chameleon doesn't have changing pigments. It has special cells with crystals that alter structure when muscles contract, changing how electrons interact with light. It's as if they were dancers capable of instantly changing dance styles. And the colors you can't see? Your retina only detects 3 types of colors, red, green, and blue, but your brain combines this information to create millions of hues. It's as if you had only 3 musical instruments but could create an infinite symphony. Electrons are creating many more colors than you can perceive. Bees see in ultraviolet, revealing patterns in flowers that are invisible to us. Snakes see in infrared, detecting the heat of warm bodies. Each species lives in its own world of colors, each tuned to different aspects of the electronic dance. And artificial colors? LEDs, computer screens, lasers. All of these are human attempts to control the dance of electrons to create specific colors. It's as if we had learned to be conductors of this electronic orchestra, directing electrons to play exactly the notes we want. But perhaps most impressive is that this entire symphony of colors exists only in your mind. Electrons have no color, they just dance with different energies. Color is an interpretation your brain creates of this dance. It's as if you were a poetic translator, transforming the abstract movements of electrons into the visual language of colors. Now let's explore how temperature affects the dance of electrons. Have you noticed how metals get hot when an electric current passes through them? How the filament of an incandescent light bulb glows when heated? This isn't an accident, it's a direct consequence of how electrons dance when they receive extra energy. Temperature, at its most fundamental level, is a measure of how vigorously atoms and molecules are moving. It's like measuring the excitement of a party. The higher the temperature, the more agitated the dancers are. And when atoms dance more vigorously, they influence the dance of electrons. At low temperatures, near absolute zero, -273 degrees Celsius, the dance of electrons becomes more ordered, more predictable. It's like a classical ballet performed in slow motion, where every movement is precise and deliberate. Under these extreme conditions, some materials become superconductors. Electrons dance in perfect harmony, with no resistance to movement. Superconductivity is one of the most elegant phenomena in physics. Electrons form Cooper pairs, dancing together like couples in an eternal waltz. These pairs can flow through the material without losing energy, creating currents that, in principle, could last forever. It's as if the dancers found such a perfect rhythm that they never got tired. But when you heat a material, the dance becomes more chaotic. Electrons begin to collide with vibrating atoms, losing energy in each collision. That's why electrical wires heat up. Electrical energy is being converted to heat through these microscopic collisions. Have you ever wondered why some materials are good heat conductors? It's because they have free electrons that can transport thermal energy. In copper, for example, electrons move quickly through the material, carrying energy from hot regions to cold regions. It's as if they were thermal messengers, balancing temperature through their dance. And the light emitted by hot objects? When you heat a metal until it glows red and then white, you're observing electrons being excited to higher energy levels by heat. When they fall back down, they emit light. The color of this light depends on temperature: red for lower temperatures, white for higher ones. Stars are the perfect example of this. A star's color tells us its surface temperature. Red stars are relatively cool, yellow ones like our sun are medium temperature, and blue stars are the hottest. It's as if each star were a symphony of electrons playing at different temperature registers and semiconductors. In semiconductors, temperature has a dramatic effect on conductivity. At low temperatures, few electrons have enough energy to participate in conduction. But as temperature increases, more electrons gain energy to jump to the conduction band. It's as if temperature were a DJ turning up the music volume, encouraging more shy dancers to join the party. This temperature dependence is crucial for many technologies. Electronic thermometers measure changes in electrical resistance caused by changes in the electron dance. It's an elegant way to use quantum physics to measure something as basic as temperature. And what happens at extremely high temperatures? When you heat a gas to millions of degrees, like in the center of stars, electrons gain so much energy that they completely separate from their atoms. You create plasma, a fourth state of matter where electrons and nuclei dance independently. In the sun, this high-energy dance allows hydrogen nuclei to fuse to form helium, releasing enormous amounts of energy in the process. It's the dance of electrons and nuclei that powers all stars and, ultimately, all life on Earth, but there's something deeply poetic about how temperature affects the electron dance. At low temperatures, the dance is ordered but limited. At high temperatures, it's energetic but chaotic. There's a delicate balance, a Goldilocks temperature, where the electron dance allows the chemical complexity necessary for life. If Earth were too cold, water would freeze and biological chemistry would stop. If it were too hot, molecules would decompose and life would be impossible. We live in a temperate zone where the electron dance is energetic enough to allow complex chemical reactions, but not so vigorous that it destroys the delicate structures of life. We're living in the middle of the silent revolution, a transformation that's changing not just our technology, but our fundamental understanding of reality. It's the quantum revolution, and it's being driven by our growing ability to control and manipulate the individual dance of electrons. Have you heard of quantum computers? They're not just faster computers, they're a completely different way of processing information, based on the strangest aspects of quantum mechanics. In a traditional computer, information is stored in bits that can be 0 or 1. But in a quantum computer, information is stored in qubits that can be 0, 1, or both at the same time. Imagine dancers who can be in multiple positions simultaneously, creating choreographies that explore all possibilities at once. That's what qubits do. They exist in quantum superpositions, allowing the quantum computer to explore multiple solutions to a problem simultaneously. But here's the challenge. Keeping electrons in delicate quantum states is incredibly difficult. It's like trying to maintain a perfect ballet performance while earthquakes happen all around. Any disturbance from the environment can destroy the quantum superposition, a process called decoherence. That's why quantum computers need to be cooled to temperatures near absolute zero and isolated from vibrations, magnetic fields, and even cosmic radiation. They're kept in a type of isolation that would make a hermit seem social, but the results could be revolutionary. Problems that would take billions of years for traditional computers to solve could be solved in hours by quantum computers. They could break encryption codes, simulate complex molecules for drug discovery, or optimize logistics systems in ways impossible today, and other quantum technologies are emerging. Quantum cryptography uses the principle that observing a quantum system disturbs it. If someone tries to intercept a quantum-encoded message, the very act of observation will reveal the spy's presence. It's as if electrons were natural guardians of privacy. Quantum teleportation, which unfortunately isn't like Star Trek, allows transferring the quantum state of one electron to another, even at great distances. It's not the electron that travels, but the information about its state. It's like sending dance instructions to distant dancers who then perform exactly the same movements. And quantum sensors? They can detect minute changes in magnetic, gravitational, or electric fields, exploiting the extreme sensitivity of quantum states. Some are so sensitive they can detect the magnetic field of a single neuron firing in your brain. But perhaps the most exciting application is in medicine. Imagine nanoparticles that can navigate through your body, guided by quantum-controlled magnetic fields, delivering drugs directly to cancer cells, or devices that can read individual electrical signals from neurons, offering new hope for people with paralysis. Quantum biotechnology is exploring how biological systems might use quantum effects. There's evidence that photosynthesis, bird navigation, and even smell might involve quantum processes. It's as if life discovered how to use the electron dance long before physicists did. Have you ever thought about this? That perhaps your consciousness, your thoughts, your memories might involve quantum processes? Some scientists speculate that the human mind might be the most sophisticated quantum computer in the universe, processing information through quantum effects in microtubules within neurons. But here's something even deeper. The quantum revolution isn't just about technology. It's changing our worldview. We're discovering that reality is fundamentally probabilistic, that observation creates reality, that separation might be an illusion. This has enormous philosophical implications. If electrons don't have defined properties until they're observed, what does that say about the nature of reality? If particles can be entangled regardless of distance, what does that mean for our understanding of space and time? Perhaps we're discovering that the universe is more like a mind than like a machine, that consciousness and quantum physics are connected in ways we don't yet fully understand, that the dance of electrons might be the fundamental choreography of existence itself. Now let's broaden our perspective beyond Earth, beyond the solar system, to contemplate how the dance of electrons unfolds on the vast scales of the cosmos. Look up at the stars. Every point of light you see is a nuclear furnace where electrons dance under extreme conditions, creating the elements that compose your body. You are made of stardust. This isn't just a poetic phrase, it's literally true. The carbon in your muscles, the iron in your blood, the calcium in your bones, all were forged in the hearts of ancient stars through the dance of electrons and atomic nuclei. In stars, Temperatures of millions of degrees force electrons to separate from their nuclei, creating a plasma where normal chemistry rules don't apply. Hydrogen nuclei fuse to form helium, releasing energy that eventually travels 93 million miles to warm your face on a sunny day. But stars do more than just shine. They're cosmic factories using extreme pressure and temperature to forge increasingly heavy elements. The oxygen you breathe was created when 3 helium nuclei danced together in the core of a giant star. The iron in your hemoglobin was forged in the final convulsions of a massive star before it exploded as a supernova. And speaking of supernovas, they're perhaps the most spectacular events in the cosmic dance of electrons. When a massive star exhausts its nuclear fuel, it collapses in a fraction of a second. The compression is so intense that electrons and protons are forced together, forming neutrons and releasing neutrinos that traverse the entire star in instants. The shock of this implosion creates an explosion that can shine brighter than an entire galaxy for weeks. It's in this cosmic cauldron that elements heavier than iron are created. The gold in your jewelry, the silver in your utensils, the uranium that powers nuclear plants, all were born in the violent dance of electrons during stellar explosions. Have you ever wondered where the energy that powers galaxies comes from? At the center of almost every galaxy is a supermassive black hole, sucking matter into an accretion disk that spins at speeds close to light. In this disk, electrons are accelerated to extreme energies, emitting radiation that can be detected billions of light years away. And dark matter? Although we don't know exactly what it is, we know it interacts very little with electrons. It's as if there were a parallel dance happening in the universe, an invisible choreography that influences cosmic structure through gravity, but rarely interacts with the electron dance we know. The cosmic microwave background, the echo of the Big Bang, is essentially the oldest light in the universe, photons released when electrons first joined with nuclei to form neutral atoms. About 380,000 years after the Big Bang. Before that, the universe was opaque to light because free electrons scattered all photons. This moment, called recombination, was when the dance of electrons took the form we know today. It was when the first hydrogen and helium atoms formed, creating the raw materials for the first stars. It's as if it were the moment when dancers found their partners for the first time. And gravitational waves? When black holes or neutron stars spiral toward each other before merging, they distort space-time itself. These ripples in the fabric of the universe can be detected by interferometers that measure changes smaller than a proton in the distance between mirrors separated by miles. But here's something fascinating. Even these detections depend on the dance of electrons. The lasers used in gravitational wave detectors are created by electrons jumping between energy levels in a coordinated manner. It's the dance of electrons that allows us to detect ripples in spacetime created by the universe's most violent events. And the cosmic future? As the universe continues expanding and cooling, the dance of electrons will change. In trillions of years, the last stars will burn out. In unimaginably long times, even protons might decay, leaving only electrons, photons, and black holes. But even then, the dance will continue. Black holes will eventually evaporate through Hawking radiation, a process involving pairs of virtual particles being separated at the event horizon. It's a quantum dance that happens at the boundary between existence and nothingness. Perhaps, at the end of everything, when the universe is cold and dark, there will still be isolated electrons dancing in their orbits around solitary nuclei, performing their quantum choreography in an almost empty cosmos. They'll be the last performers of a symphony that began with the Big Bang, or perhaps the dance is eternal in other ways. Perhaps there are multiple universes, each with their own rules for the electron dance. Perhaps what we call reality is just a small part of a much larger cosmic dance, with dimensions and possibilities we can't yet imagine. We're approaching the end of our journey, but before we bid farewell, let's reflect on the deeper meaning of the electron dance. There's something profoundly poetic in discovering that all the complexity of the world emerges from simple, elegant rules governing invisible particles. Think for a moment about your own existence. You began as a single cell, the result of two other cells joining, but this story goes much further. The atoms that compose your body traveled through space for billions of years before meeting in you. They participated in countless other dances, in distant stars, in ancient rocks, in plants and animals long extinct. The electrons now dancing in your neurons, creating the thoughts you're having at this very moment, are the same electrons that once danced in the heart of a star. They carry with them the cosmic memory of journeys across galaxies, of transformations in supernovas, of billions of years of chemical evolution. Have you ever stopped to consider that your thoughts are patterns in the dance of electrons? That consciousness might be a particularly complex choreography of this fundamental dance? Every memory you form, every decision you make, every emotion you feel, all of this can be seen as different arrangements in the great electronic symphony that is you. And there's something wonderful in discovering that you're not separate from the universe. You are the universe knowing itself through the dance of electrons. When you observe a star, it's electrons in your retina dancing with photons that traveled light years to reach you. It's literally the cosmos observing itself. Quantum mechanics teaches us that observer and observed cannot be completely separated. Your consciousness is entangled with the reality you observe. Perhaps existence itself is a collaborative dance between mind and matter, between consciousness and cosmos and creativity. Where do inspiration, art, music, poetry come from? Perhaps they're high-level manifestations of the fundamental creativity that resides in quantum uncertainty. Perhaps the same randomness that allows electrons to create new patterns is what allows the human mind to create beauty and meaning. Have you ever wondered why mathematics describes the universe so perfectly? Why Schrödinger's, Maxwell's, and Einstein's equations capture the essence of reality with such elegance? Perhaps it's because the human mind itself is a product of the cosmic dance it tries to understand. We are the universe developing language to describe itself. And love? It might seem strange to think of love in terms of electrons, but consider this. Every emotional connection you feel is mediated by chemical reactions in your brain, which in turn depend on the dance of electrons. When you feel love, compassion, admiration, or joy, there are specific patterns in the electronic dance that create these experiences. This doesn't diminish love. On the contrary, it reveals that even the deepest and most meaningful experiences have their roots in the fundamental choreography of the cosmos. Love is one of the ways the universe connects with itself. And the search for meaning? Perhaps meaning emerges naturally when complex patterns in the electron dance become capable of reflecting on themselves. You are a pattern complex enough to question your own existence, to seek beauty, to create art, to love. There's also something humbling in realizing that you're made of the same fundamental particles that compose a rock, a star, or an amoeba. The only difference is the pattern of the dance. You're not special for being made of unique materials. You're special for the incredibly complex and beautiful pattern these common materials have assumed. And when your individual dance comes to an end, the electrons that compose you will continue dancing. They'll join other dances in other plants and other animals, perhaps one day in other conscious minds. In this sense, you are immortal, not as an individual pattern, but as a participant in the eternal dance. Perhaps death is just a change of music, a transition to a new choreography. The dancers continue, only the steps change. And perhaps in some deep sense, the information that you are, the specific organization that defines your consciousness, is preserved in ways we don't yet understand. The dance of electrons teaches us that nothing is truly isolated. Everything is connected, entangled, participating in a unique cosmic symphony. You breathe atoms that were once part of dinosaurs. You're warmed by light created in the sun's core. You are made of stars, literally. And so we come to the end of our journey through the invisible dance of electrons. But actually, there is no end, just a pause in our contemplation of a performance that never stops. At this moment, as you read these words, trillions of electrons are dancing in your eyes, processing the light that carries these ideas. In your brain, billions of other electrons are creating the neural patterns that correspond to understanding, reflection, perhaps wonder. You now know the secret behind everything you see, touch, and experience. The solidity of the chair you're sitting in is an illusion created by the coordinated dance of electrons that refuse to occupy the same space. The color of the screen you're reading is the result of electrons choosing which frequencies of light to absorb and which to reflect. The oxygen you just breathed participated in a complex dance in your lungs, where electrons in hemoglobin change their configuration to capture and transport the molecules that keep you alive. The food you ate today was solar energy captured by the photosynthetic dance of electrons in plants, and the electricity that might be lighting the space where you are. It's literally a river of electrons flowing through conductors, obeying quantum laws they've followed for billions of years since before Earth existed. But perhaps most extraordinary is this: you're now part of the story of the electron dance. Your knowledge of this dance has changed you, added new neural patterns, created new connections. The electrons in your brain reorganized during this journey, and this reorganization is permanent. You're not exactly the same person you were when we began. And when you share this knowledge, when you tell someone about the invisible dance that sustains reality, you'll be propagating patterns of electrons from one mind to another. Ideas are contagious because they're patterns in the electronic dance that can replicate through communication. Have you ever thought about this? That all human culture, every tradition, every story we tell is a way of preserving and transmitting specific patterns in the electron dance? That books, paintings, music, movies are all methods of temporarily crystallizing dancing patterns in forms that other minds can recognize and absorb? Science itself is a collective effort to understand the cosmic dance. Every discovery is a new dance step we learn. Every theory is new music we can dance to. And you, having embarked on this journey of understanding, are now part of this great human enterprise of knowledge. But the journey doesn't end here. Each day brings new discoveries about the electron dance. Quantum technologies are emerging that would seem like magic to previous generations. New materials are being created atom by atom, electron by electron. Perhaps one day we might even control consciousness by directly manipulating the electron dance in brains. And there are so many mysteries yet to solve. How exactly does consciousness emerge from the electron dance? Are there other types of dance in dimensions we can't perceive? What happens to information when it disappears into a black hole? Is the electron dance deterministic or truly random? Look around you now with your new eyes. See the invisible dance happening in everything. In the plant by the window, capturing sunlight. In the metal of the lamp, conducting electricity. In the glass of the window, transparent because its electrons let visible light pass without interference. In the air you breathe, where electrons and oxygen and nitrogen molecules vibrate at specific frequencies. You're now a conscious observer of the cosmic dance. You know that when you touch something, you're not really touching. It's the electric fields of electrons in your fingers, repelling the electric fields of electrons in the object. You know that when you see a color, you're witnessing a choice electrons make about which frequencies to absorb and which to reflect. And perhaps, most importantly, you know you're not separate from this dance. You are the dance. You're a temporary but magnificently complex pattern in the eternal choreography of electrons. You're the universe dancing in the form of a consciousness capable of contemplating its own dance. Tonight, when you look at the stars, remember that the light touching your eyes began its journey in stellar cores, where electrons danced under extreme conditions to create the photons now dancing with electrons in your retina. You're literally connected to the cosmos through the dance of light. And when you wake up tomorrow, know that every breath, every heartbeat, every thought will be another movement in the infinite dance. You carry with you now a new perspective on reality, the understanding that everything is movement, everything is music, everything is dance. The invitation is always open for you to delve even deeper into this dance, study physics, chemistry, biology, explore how electrons dance in superconductors, in crystals, in complex organic molecules, discover how they can be manipulated to create technologies that seem impossible today, or simply remain in quiet contemplation of the fundamental beauty you now know permeates everything. Every sunset is a lesson about light absorption and scattering. Every song you hear is carried by pressure waves that make electrons dance in your ears. Every hug you give is an encounter between trillions of electric fields in harmonious dance. The dance of electrons teaches us that beauty is everywhere, just waiting to be perceived. It shows us we're all part of something infinitely larger and more elegant than we can imagine. It reveals that the universe isn't a cold, purposeless machine, but a vibrant symphony of creativity and possibility. And perhaps in the end, this is the most important lesson, that knowledge and wonder can walk together. That understanding the mechanics of the dance doesn't diminish its beauty, but amplifies it. That science isn't poetry's enemy, but its partner in revealing the hidden magnificence of the world. Thank you for accompanying me on this journey through the invisible dance of electrons. Thank you for opening your mind to contemplate the mysteries that unfold in every atom of your existence. Thank you for becoming a conscious observer of the cosmic symphony. The dance continues, infinite and eternal. And you, now and forever, are part of it? But before we part completely, let me ask one final question, one that might accompany you far beyond this narrative. If all reality is fundamentally a dance of particles following elegant and mysterious laws, and if you're a conscious manifestation of this dance capable of contemplating your own existence, what does this mean for the purpose of your life and for the role you choose to play in the grand cosmic choreography?